This is Advanced Autonomy. I'm Luke Renner. One of my favorite things about working in this space is that we are at the very, very beginning. And there are still tons of problems in the autonomous vehicle sector that we're trying to solve. So these problems span all areas of in-vehicle technology to, wider infrastructure communication. My guest today is the VP of Engineering and the Head of Autonomy at Cyngn, a self-driving industrial vehicle company that we both work for. In this conversation, he's going to give us an engineer's insider look into the three main problems that autonomy is yet to solve: occlusion, which is seeing beyond blind spots; prediction; and the coordination of a networked vehicle fleet. Hi, Biao. Welcome back.
Hey, Luke. Happy to be back.
So let's dive into those. The first one you wanted to talk about today was occlusion. What is occlusion?
Occlusion is there is a third object in between you and the target object you're trying to perceive. If you have one object you're trying to perceive, for some reason there's a different object in front of you.
Mm-hmm.
So that view is blocked. So this will have technical impact on a series of subsystems in autonomy.
So occlusion is a middle object blocking the view of the driver or the autonomous vehicle seeing another object.
Yes. It could be a moving object. It could be a static object. It could be a vehicle, a tree, or a building.
And this is a problem because just like humans can't see through trees, a lot of our sensory technology also can't travel through objects.
Yes. So most of the sensors are bounded by light travel straight. And there are certain technology being developed to have certain level of penetration.
Got it. So occlusion is not only about making it easier to see, it's also about making it easier to understand when you can't see.
Yeah.
Is that also true?
That's true. The two sides of this. The second angle of that is in certain scenario, you should have the capability to anticipate or expect something might happen or some object might be there. So it should be built in your system.
Okay, so this is clear. So what are researchers doing to try to solve the problem of occlusion?
There are basically two branches of exploration and effort try to pushing the technology forward.
Okay.
One is really about how do you see beyond the line of sight? Basically, yes, we know light travels straight, and there's not really a good way to change that. And there are methods and systems could be explored to see beyond that. For example, you have a collaborative perception, and you have a fleet or a crowd of perception points that could contribute to one and better perception.
So you're talking about using the other cars on the road to see for the other cars on the road.
Don't have to be cars, right? It could be a different perception unit providing that to you. Maybe in the corner of the street, which will be a school area, you have an intelligent light pole are sending perception, either info or object or raw data to you, right? So that really give you not only one eyes looking, but also a crowd of eyes looking at the street.
So that's one way. You said there were two ways that researchers are trying to solve the occlusion problem. What was the other way?
So the second one going towards a different direction. One is about how do you see them? The second one is about, even though you don't see that, can you be smarter to anticipate there will be danger, will be objects that you need to respond to?
So the second branch is training the vehicle to develop an intuition about things that it can't see.
Yeah.
And humans do this really naturally, right? Like around a schoolyard, we know to slow down. When we're driving over a mountain pass, we behave differently because a deer could jump in front of the road at any moment. And so it's about kind of giving the autonomous vehicle some of that intuition and some of that intelligence.
Exactly. There's always a constant trade-off of responsiveness and the stability, right? So you can't really achieve both. You want to make sure your system have certain level of responsiveness, just as you described. A car come out of nowhere. You need to be able to quickly respond to that. On the other hand, you cannot be fragile. It cannot be a driving system that is constantly changing because of things that may be relevant to you, right?
Can't be a scaredy cat driver.
Exactly. Yeah. Can be a scary cat. Yeah.
Okay, so this is really interesting. Let's transition to the second major obstacle, predictions. So before we get into why predictions are so difficult, I'd like you to actually define what you mean when you say prediction.
Prediction is predict the trajectory of a target object in the coming frames, typically 3 to 5 seconds. Trajectory meaning the location and the speed of the perceived object.
So it's about looking at objects that are moving and guessing where they're going to be in a few seconds later. Is that right?
Yes, and it could be one or many trajectories as predicted.
So making predictions not only includes where the object may be headed, but also a range of possibilities of where the object could head. Human drivers know children are far less predictable than adults. So driving by a kid probably necessitates greater care. So in that situation, presumably the AV takes in information of its surroundings, runs that through AI processing, and uses all of this to make a decision. So can you give us a little bit of insight into how this is actually possible? Show us under the hood.
There are 3 key technical factors for prediction. One is really about the semantic. Semantic is the meaning bounded by the environment or a segmented environment that you are driving. For example, this lane is left turn only lane. That lane is straight only lane. So basically you can see is the common rule that is bounded by either the traffic or social convention or a specific area of the targeted driving space.
So it's the context. So it's the way we can drive on a 2-lane highway and not freak out when a car passes us.
Yeah, exactly. So you have a 2-directional highway. Even though the upcoming vehicle is close to you and relatively fast, the vehicle or the system shouldn't freak out because the semantic is saying that is an opposite direction.
All right, so that was the first one. And you said there were a couple others. What are they?
The second is the objects are, end of day, bounded by physical limitation. Sometimes we talk about there's no Superman, right?
Okay.
So the kid may be highly unpredictable in terms of movement, but the kid don't fly.
So the system is able to differentiate between like a car that could go 60 miles an hour to you versus a child who cannot.
Exactly.
Okay. And then what's the third?
And the third one is under the hood, there are at least 3 layers. One is relevancy prediction. So relevancy prediction is there are many objects around me, right? So a lot of time, half of the objects is nearby, but not important, not relevant at all. So how do you differentiate? How do you predict this is relevant, that is not relevant? For example, you are taking a right turn at the intersection. There are objects in front of you taking a different right turn. Both of you are taking a right turn. You are not relevant to him. That object is not relevant to you. Relevancy prediction is the first layer. The second one are the prediction based on trajectory, using the current motion of the target object, right, with the current velocity of the object. So if this object will be important for you to alter your trajectory. And the third is really about, okay, there is a significant either cross point of your trajectory, you have to respond with certain confidence, or there are other implications of the object by the nature of the classification or implication of the place you are driving at, right? There is a little ball in front of you. Do we have the intelligence to anticipate maybe there is a little boy because this is a school area, right? So that is, again, this is a topic to be further explored and implemented.
So just to make sure I understand. So the first thing is there's a lot of objects in the space. So the first filter is the object anywhere near us and relevant? The second filter is the object moving toward us in a way that could be relevant? And the third is there some context around that object that might make it behave in a way that requires additional caution? Are those kind of the three filters?
Simply speaking, yes. And in terms of methods to do this, there are learning-based method for a component of that. We can call it predictor or evaluator, right? So to predict, or there will be specific algorithm-based, optimization-based, or rule-based, right? So the different way to do this, and this is really an interesting area to be further developed.
Got it. So how good are we at predictions now?
A simple answer to that is they are significantly advanced in this area and is not good enough yet. What I mean by that is there are mechanisms regarding the semantic layer of the high definition map, for example. There are learning-based methods try to provide prediction with certain input, and there are algorithms implemented based on the semantic and the motion of prediction. So different prediction mechanisms require the upstream system to align and require the downstream system to use the information of the predicted trajectory.
Yeah. So I'm wondering, like, how are AV researchers going to know that their algorithms are actually getting better at prediction?
Think about if you set back the time in 5 seconds in your data using your tool or your infrastructure to do that, you actually get a ground truth of the trajectory that object will do in the coming 5 seconds. So this ground truth can give you a good way to evaluate how good you are on predicting that. You have one ground truth trajectory, you have one predicted trajectory, right? So that gives you a ground truth.
You compare what really happened to what your system expected would happen and see how close those two are together.
Yes.
So what are researchers doing to help their autonomous vehicles get better at making predictions?
There are at least 3 directions, as I can see in the industry. Number one is to reduce the need of input. What I mean by that is some prediction systems require the knowledge of the semantic or require the certain classification provided to it. To predict what the object will do, the upstream system need to tell this is a pedestrian, this is a motorcycle. So that assumption could be reduced, so prediction could be smarter in a simple way. The second angle is, given the setting of input and output, how this prediction could improve given higher confidence, given higher granularity, or produce not only the trajectory, but also the higher level information what the vehicle is trying to do. For example, not only the vehicle is going this direction, if we can predict in a better way, this vehicle is trying to take a left turn, right? Or the vehicle is trying to do a lane changing, right? So there are more behavior level prediction can be used to help the ego vehicle drive better, right? So not only the direction or the raw information, but also at a higher level. That's the second. The third is about technical direction wise, the best prediction is communication. No matter how good you are at predict what I will do, the best one is I will tell you what I will do, right? So actually think not only prediction as one subsystem. If we look at the holistic view of the whole stack, there are modules or subsystems can grow together.
This is all very fascinating. So we've covered occlusion, we've covered prediction. Let's talk about the final challenge, which is fleet planning and control. So my question for you is, what is fleet planning and control, and what makes it different from regular autonomous vehicle development?
The initial phase of autonomy development is really about a challenge. Can we make a car self-drive? Right? That's the whole idea behind the initial development and the initial bring up of autonomy settings using the initial set of sensors and get the proof of concept. The second phase is really about how do you scale up. There are algorithms being proposed and developed for considering the coordination of a fleet, right?
Mm-hmm.
Instead of each of the vehicle need to perceive and track and predict what you will do, the algorithm in a centralized way or in a way more efficient way will provide this to the fleet. So that gives the new opportunity to getting things done in a more effective way.
So last time you were here, I asked you to make predictions, and I'm going to ask you to do it again. So of the three things that we talked about, occlusion, prediction, and fleet management, which of these problems do you think will be solved first?
I don't think it will be solved one after the other.
Okay.
Solving prediction, occlusion, fleet scale actually require a whole new generation of autonomy stack. Each of the subsystems need to work together. So I do think they will be solved down the road together with new generation of design and methods.
And how long do you think it's going to take?
I'm optimistic. So I do think in the coming 3 to 5 years, there will be significant improvement coming to occlusion, prediction, large-scale decision planning and control.
All right, Biao, I appreciate the time. Thanks so much. It was interesting.
Great. Yeah, very happy to be here.